Good morning, students. Today we are going to solve the homogeneous integral equations or the solution of the homogeneous Fredholm integral equation. How to solve a homogeneous Fredholm integral equation. So for this one, solution of homogeneous Fredholm integral equation. How to solve a homogeneous Fredholm integral equation? The method for the solution of these type of the problems, we will start with a problem that you have to solve the homogeneous integral equation, and the equation is given as phi x is equals to lambda integral 0 to 1 e raised to x e raised to t phi t dt. The problem is given that phi x is equals to lambda integral 0 to 1 e raised to x e raised to t phi t dt. We have to solve this type of the integral equation. The solution of such type of the problem starts with, here we see that the kernel of this problem or is of this integral equation is e raised to x e raised to t. We can separate the kernel in terms of the functions only of x and only of t. So these type of the problems are the problems with separable kernels. So we can separate the kernel in the variables of x and t. So this equation can be written as, equation 1 can be written as phi x is equals to lambda e raised to x integral 0 to 1 e raised to t phi t dt. We can separate the kernel. Now this can be written as, this is lambda into c into e raised to x number 2, where c is equals to integral 0 to 1 e raised to t phi t dt number 3. So the solution of the problem homogeneous integral equation is given by the equation number 2. So the solution of this problem, phi x is equals to lambda c e raised to x. Our task is to find the value of the constant c, where the value of c is given as integral 0 to 1 e raised to t phi t dt, where phi x is given as phi x is equals to lambda c e raised to x. So our task is to find the value of c. So for the value of the c, putting the value of phi t from 2 into 3, so using 2 in 3, we get c is equals to integral 0 to 1 e raised to t phi t is from equation number 2 is lambda c e raised to t dt, or we can say that this c is equals to lambda into c integral 0 to 1 e raised to 2t dt. Integrating this one, we get lambda into c e raised to 2t upon 2, and the limits are from 0 to 1. Putting the value of t, we get lambda into c by 2 into e raised to 2 minus e raised to 0, that is 1. So here we get the value of c. So c into 1 minus lambda by 2 into e square minus 1 is equals to 0. Now as we see that if C is equals to 0, if C is equals to 0, then phi x is equals to 0, and phi x is equals to 0 is the trivial solution. Now if we seek the non-trivial solution of the given homogeneous equation, which is non-trivial solution, that is possible only when C is equals to 0. So for non-trivial solution, of 1, C should not be equals to 0. If C should not be equals to 0, then this value is equals to 0. Then 1 minus lambda upon 2 into e square minus 1 is equals to 0, which gives the value of lambda. So lambda is equals to 2 upon e square minus 1. Lambda is equals to 2 upon e square minus 1. Which is the lambda? What is lambda? Lambda is the value of the eigenvalue. So which is the eigenvalue. So putting the value of lambda in equation number 2, we get the required solution of the problem. So putting the value of lambda in 2, we get phi x is equals to lambda c into e raised to x. Lambda c, that is c into lambda, that is 2 upon e square minus 1 into e raised to x. Phi x is equals to c into 2 upon e square minus 1 into e raised to x. So this is the constant. This is the constant. If we set 2c upon e square minus 1 is equals to 1, then phi x is equals to e raised to x, and phi x is equals to e raised to x is the required eigenfunction corresponding to the eigenvalue or this required solution of the problem. So phi x is equals to e raised to x is the required eigenfunction corresponding to eigenvalue lambda is equals to 2 upon e square minus 1, or we can say phi x is equals to e raised to x is the required solution of the homogeneous equation, which is the required solution of the given homogeneous integral equation. Thank you very much.